Welcome back to ECE 501B. Homework number 4 is due in a couple of weeks, and that should give you plenty of time for that, but then they will actually come in pretty rapid succession before our next exam, so you might want to be working ahead on homework number 4. You should be able to access the solutions to exam number 1 at 5:30 today, Tucson time. And what I want to cover today is pick up where we left off before the exam. I guess that was a week ago with Chapter 5, which is dealing with eigenvalues and eigenvectors. We'll recap the examples, the 3 examples that we began with or just illustrated these concepts of eigenvalues and eigenvectors. We will look at a particular matrix that doesn't have real eigenvalues and what that means. Then we'll spend some time talking about invariant subspaces. And invariant subspaces, right now you might just think eigenvector. That's one way of thinking about an invariant subspace. Then we will just sort of state some facts about invariant subspaces, and that really pertains to the null space of an operator, the range space of an operator. Then we will go through some definitions, and I think I will just post on D2L a few pages of write-up on how you might find eigenvalues and eigenvectors without using the determinant. It's a more algebraic approach to trying to find this characteristic polynomial that we don't yet know exists in that form. We're not going to use the determinant. That's in Chapter 10, and we're not there yet. We're in Chapter 5. So this book is linear algebra done right, which means don't talk about determinants until the very end. With that in mind, we have to, that's why I'm giving you this sort of procedure or these steps in how to find eigenvalues and eigenvectors based on how we can do that at the present time. Again, we're in Chapter 5, and from before we said if we can find these vectors v and these scalars lambda that satisfy this equation, then we have identified an eigenvalue and an eigenvector for that operator or that matrix A. Again, operators are going from some subspace and staying in that subspace. And now if you want to think about operators, you might think Las Vegas. What stays in Vegas, or what happens in Vegas stays in Vegas. Here, what starts in a subspace stays in a subspace if you're dealing with an operator on that subspace. I don't know, that I was writing up some notes and that sort of popped into my head. That might be a way for you to think about an operator. Here are the matrices that we talked about last time. And we looked at a diagonal matrix where the eigenvalues are staring you right in the face. They're right on the diagonal. We looked at an upper triangular. Again, the eigenvalues are clearly identified as being on the diagonal. And then we looked at a dense, or something that doesn't have very many zeros. It's not a sparse matrix. And in fact, that particular matrix also had eigenvalues at -1 and -2. Now, what I want to start with today is a matrix that actually does not possess real eigenvalues. And you'll start to see that this structure actually is telling you already where the eigenvalues are for this 2x2 matrix. We will start to become more comfortable with block upper triangularizing or block diagonalizing matrices, and we'll be working with scalar blocks or blocks that are 2x2. And when we do not have real eigenvalues, if we're dealing with real coefficients or real elements in our field of numbers, then we might have 2x2 blocks that look like this. We are going to show that the eigenvalues for this C matrix are in fact having a real part of -1. Those are on the diagonal. But the off diagonal in this 2 by 2 give us the imaginary component of those roots. These eigenvalues are at -1 plus and minus j2. And you can see those immediately from this particular structure once we've shown where that might come from. Let's then go through that quickly so that we can believe that in fact this particular matrix does not possess real eigenvalues. If we start with the eigenvalue eigenvector equation, that then says that we have Cx is equal to lambda x, and we're looking for a vector x. In this case, x, I'm really overusing x, but x now is a column vector that's 2 rows tall or 2 components tall, and lambda is a scalar, and we're trying to determine is lambda a real number for this matrix or not, and in fact it will not be. But if we start with this eigenvalue eigenvector equation, that will allow us to then say that we have C minus lambda I times x is equal to 0. We can just move lambda x to the other side, and we can factor out the vector x by inserting this space holder, this identity matrix. That capital I is 1 on the diagonals and 0 off the diagonals. That's what the capital I means. Or we could, it doesn't matter if we have this equation or its opposite sign form, we could negate that and we still have it equal to 0. And sometimes it's easier to keep lambda with a positive coefficient than being subtracting this variable. Let's then start with this lambda I minus c. We have lambda then on the diagonal, and then we simply subtract c from that. And subtracting c, we end up with +1 on the diagonal, and then we have a -2 and a 2. Now let me explicitly identify the components of my vector x. And this now gives me 2 equations in these different unknowns. I have an unknown lambda, and I have unknown components to my vector x. I have an x sub 1 and an x sub 2. If I look at the first equation, I have lambda plus 1 times x1 minus 2x sub 2 is equal to 0. That's the top row, or the first equation. And I also have 2x sub 1 plus lambda plus 1 x sub 2 equal to 0. Suppose that I'm trying to now find an equation that lambda will satisfy. Let me play with the second equation and actually solve that for x sub 1. So I can push the x sub 2 term to the other side and divide by 2, and I end up then with x sub 1 being minus 1/2 lambda plus 1 x sub 2. What I want to do now is actually put this in there. And then I will have one equation in x sub 2. Meaning, if I do that, I can now say that I have the following relationship for lambda, and it includes x sub 2. I have a minus 1/2 lambda plus 1, and I have this lambda plus 1 also, and that's all times x sub 2. That's by substituting this right-hand side in for x sub 1, and then I have a minus 2 x sub 2 equaling 0. If I now multiply through by, let's say, -2, I can clean up that -1/2 in the front, and I'm left with lambda plus 1 squared x sub 2 plus 4x sub 2 equaling 0. I can factor out x sub 2, and I have a lambda plus 1 squared plus 4 x sub 2 is equal to 0. And I want a non-trivial solution to this set of equations, which means I want x sub 2 to be non-zero. I can divide that out, and now I know that what's in the square brackets has to equal 0 if this product is 0. Which means I'm looking for a lambda, and we started with asking, can we find a real number lambda that will satisfy this system of equations? We're now asking that question, is there a real lambda, or is there a lambda that lives on the real numbers or in the real numbers such that lambda plus 1 squared plus 4 is equal to 0. And that will allow us to then satisfy that equation when x sub 2 is not trivial, when x sub 2 is non-zero. Can you find a lambda that will make that equation happen? A real number lambda? No, we can try to minimize that equation, but it's not going to get all the way down to 0. Both of those terms are positive. 4 is a positive number. Lambda plus 1 is squared. That's positive. We can make lambda plus 1, that term, 0 by setting lambda equal to -1, but that's as good as we can go in terms of trying to get us to 0. There's no way that we can make that equal 0. We can see that this is always greater than or equal to 4, which is greater than 0. And if you wanted to think about it more, let's say, pictorially, if this is now lambda, and here's 4, then if we, and this may not be very accurately drawn, but now we have something that will be 4 when lambda is -1, and then it just grows from there, and it's growing quadratically. Like I said, this is not a very accurate sketch, but you get the idea. We wanted that to have a real solution for lambda. We needed that to go through, or to have that a lambda such that that blue curve could be equal to 0, and it's not. But we can look at the roots of that. Okay, so we can't find a real number that solves that. Let's now open up our field of numbers. We now can say, okay, if we allow for lambda to be complex, now we can say, okay, I really need something when it's squared to give me -4. And that's obviously then telling us that when we square a number and get a negative, we're dealing with complex numbers. If we take the square root of both sides, we can then take the square root of -1. That's plus and minus, and we have both pieces. We have a plus and a minus, square root of -1, and then square root of 4, which is 2. And this is now leading us to what we said we were going to end up with. If I now subtract 1 from both sides, I now see that lambda is -1 plus and minus j2, which is in the complex number, or is a complex number, or those two are in C, and consequently we do not have real eigenvalues for this particular matrix C, which was -1, 2, -2, -1. And I hope then that what that's telling you for a fact now is if you're dealing with a 2 by 2 matrix, it may not have real eigenvalues. You may not be able to find real eigenvalues for a 2 by 2 matrix. Which means that this answers one of the questions that a faculty member posed of us when I was your age or in your position. Let's not talk about age. But when I was in your position, a faculty member gave us a homework assignment and he basically said, tell me all you can tell me about this matrix. And he gave us a generic 2 by 2 matrix. I had no idea what he was asking. But essentially, he was wanting us to show the different possible eigenvalues that you could have for this 2 by 2 matrix. You could have two real eigenvalues where those real eigenvalues could be equal, they could be unequal, or you could have complex conjugate eigenvalues. And we needed to show a little bit more than that, but that's sort of the bottom line. So realize that for a 2 by 2, you are not necessarily always going to have real eigenvalues for that matrix. Let's now start to formalize these ideas of eigenvalues and eigenvectors a little bit more. Based on the material in the textbook. And what we're doing now is starting to build up our knowledge of operators. And what are operators? They are something that start in a vector space and return to that same vector space. And so when these operators dealing with finite dimensional systems, we now have, if we look at their matrix representation of these linear operators, we now have a square matrix. So now we're looking at what's going to happen when we deal with these square matrices and, in fact, these operators. We are going to assume that these vector spaces, V, is always a non-zero finite dimensional vector space, at least when we're talking about this material in Axler. When we get beyond Axler, then we'll open it up and have infinite dimensional vector spaces. And we are going to, again, continue to keep F as our field of numbers, where F could be either the reals or the complex numbers. And I need to switch colors because this is actually the heart of the class. So now we're thinking about hearts. We're in red, and this is a key part of this class, and what we're trying to do is we're trying to understand what we can learn or have available to us with respect to the structure of linear operators. And the notation is this linear map T is in this linear map from V to V, and we just abbreviate that as V. Now, to get us thinking about operators, which are mapping from a subspace back into the same subspace, let's now return to some concept that we've already introduced, and that is a direct sum decomposition of a vector space. A useful place to start is by considering our vector space as having a direct sum decomposition. Which means what? If we now have our vector space V, we are now breaking that up into subspaces. And each subspace, let's say U sub 1, U sub 2, these are now non-overlapping subspaces. That's this direct sum idea. They do overlap at the zero vector, but that's their only overlap. And let's say that we now have n of those. Since we were talking about Las Vegas, we have Nevada subspaces, little n. And do we remember what that means? If I give you a vector, little v, in your vector space, capital V, what does having a direct sum decomposition allow us to do or to say? Okay, we can only come up with one combination of vectors in these subspaces that will combine to produce this little v. So we can represent little v as some sum of vectors coming from each of these subspaces. That is, every element, think vector, in our vector space V has a unique decomposition in terms of elements of the various subspaces. Or every vector space, or what we can then also make a comment of, is that every vector space has a decomposition like this, or a direct sum decomposition. Now, it could be sort of the trivial decomposition where you have the zero vector and the whole space, but that's a direct sum decomposition. Although it might be the trivial v is equal to v plus 0. Now that we've split this vector space into these non-overlapping subspaces, let's see what happens when we operate on those with a map. So let's now, since we have split V into non-overlapping subspaces, the only place they do overlap is the zero vector. So except for 0, and that's one of the properties of a subspace, it has to contain the zero vector. All these subspaces contain the 0, we can think of T, this is our linear map, as acting on each of these subspaces in our direct sum decomposition independently. Meaning we're trying to see what can we learn anything if we now have a u sub 1, one of these subspaces, and then we operate on u sub 1 with this linear map T. Ideally, it would be an operator on u sub 1, but we can't guarantee that. But we want to know if we now have this direct sum decomposition, when can we assume that that linear map will act as an operator on each of these subspaces? And Axler, in the notation of the textbook, uses the following notation. We have our linear map T, and then we have a long vertical line, and that's now linear, or a linear map restricted to u sub j. Meaning that's how we'll basically write T restricted to the subspace u sub j. And the unfortunate thing about this isn't as helpful as we might hope, since there is no guarantee that this linear map restricted to this subspace u sub j is an operator on u sub j. That is, that operator, or it, might map vectors or map some vectors to other subspaces. Meaning we might have a vector in u sub 1, we apply the linear map to that vector, and boom, the result may not end up back in u sub 1. That's what we're trying to say. Let's look at an example of that, which is a fairly straightforward example, but I think it will start to make it a little bit more clear what we're meaning by a linear map being an operator on these subspaces in the direct sum decomposition. Suppose that our vector space is R3, so now we have the room, X, Y, and Z, and we need to come up with some subspaces to do a direct sum decomposition. Let's just think of the basic or the standard bases, the x-axis, the y-axis, and the z-axis. Those are form a direct sum decomposition. So let's let subspace 1, U1, be the x-axis. Let's let capital U sub 2 be the y-axis, and U sub 3 be the z-axis. And I think then it's clear that this R3, the vector space V, is U1 plus U sub 2, with the sum being the direct sum decomposition, or the direct sum notation. V is U1 plus circle U sub 2 plus circle U sub 3. Since any vector in V can be written uniquely as, let's say, V sub 1 equaling U plus V plus W, with U belonging to U sub 1, V being the component in the y direction, and W being the component in the z direction. We have R3. We've done a direct sum decomposition. We've identified 3 subspaces, the x, y, and z axis. Now let's look at a map that may not allow for it to be an operator on these particular subspaces. Now consider the map T that operates on, let's say, this 3 vector x, y, z, and suppose that the output of that, you give it an x, a y, and a z component in R3. It's an operator, so it now needs to map back into R3, but suppose that the result is minus y x z. What kind of a linear map is that? So now you might start building something up with your hands. You have an x, a y, and a z, and what's happening? The x coordinate now becomes the y coordinate. The y coordinate now becomes the minus x coordinate, and z stays. So if we were living, so z, we don't have to worry about the vertical. We can just play on the floor. This is now the xy plane. Now I start at x, and where do I go? I go up to y. And where did y go? To minus x. So what's happening with that xy plane? Do you see that it's just sort of rotating? It's rotating 90 degrees counterclockwise. Is that right? This is now, let's just say this is a 90-degree counterclockwise rotation in the xy plane. That's what this linear map is. Is that okay? So I'm starting at x, and then I go from x, I go to y, and my y goes, is that going against a clock's hands? That's how I'm seeing it. So if we had an analog clock, then if the x-axis was at 3, it's going to midnight or 12. Y would be at 12. It's going to 9, isn't it? Pardon? Y goes, or X, if I'm sorry, y, y goes to minus x. So if y was at 12 o'clock, then it's going over to 9. So draw it on a piece of paper and see if it makes sense. I hope it does. And draw a dot on the y-axis. So now what I'm saying is you now have, maybe I should just, instead of talking about it, let's say that we started right here with y. Where does y move to? With this map that we're saying, it ends up there. That's the new x. The old y, if we wanted, I'm sorry, the original x was, let's say, here. This is really going to get confusing, but where does it go? X now becomes y. So that now the red right angle becomes the blue right angle, and it's a counterclockwise rotation of 90 degrees. That's the idea behind that picture. So now let's see what that means if we started with a vector in one of these subspaces that we've done our direct sum decomposition into. Suppose that we consider applying this linear map T and restricting that to U sub 1. Now what happens? Now we say, oh, let's start on the x-axis, and by this linear map, I don't know if I can collapse it, where do I end up with? If I start at 3, 0, 0, where do I end up? I end up at 3 on the y. Now, did I stay in U1? Did I stay on the x-axis? No. So this linear map is not an operator on U1. You start in U1, you don't return to U1. It's an operator on R3, but it's not operating in these restricted these reduced subspaces in R3, in this direct sum decomposition. Let me try to wrap that up. T, the linear map, is not an operator on U sub 1. Now, T is an operator where? On R3. But it's not an operator on this restricted space or subspace within R3. And here's, I guess, where I came up with my phrase that I started with when we were talking about the goals. One of the goals was what starts in U1 does not stay in U1. That's what I was meaning by when we were talking about this. Think Las Vegas. What happens in Vegas stays in Vegas. Well, here, what started in U1 may not stay in U1, and it really is critical what that linear map is. Okay, so now what we wanted to do, we want to have an invariant subspace on these subspaces within the vector space V. And I hope that you now see that these invariant subspaces are special objects. We can't just arbitrarily do a direct sum decomposition and say, oh, that's going to work. This idea of a restricted operator being an operator on the restricted subspace it's not only a special idea, but it's very important. And that's why we've introduced this new terminology. We call a subspace where this behavior is true, where we do start in a subspace and we use that linear operator and we end up back in the subspace. We call a subspace where this behavior is true an invariant subspace under the linear map T. So an invariant subspace means that if we start in that subspace, we operate on that vector in or with that linear map, we end up back in that same subspace. That's an invariant subspace under a particular linear map. Or, said another way, or that is, given a linear map T, let's say on a vector space V, and U a subspace of V, this subspace U is invariant under T if, when we pick any vector little u in this subspace capital U, then that subspace capital U is invariant if no matter what we pick as a vector in that subspace, that actually implies that TU remains in U. Or that is T restricted to U is an operator on U. Let's now look at an example from the textbook that will take us outside of R3. So we'll no longer be right now restricted to this three-dimensional space. Suppose that we now have a vector space V that's P sub 7 of R. What's that? Script P sub 7 of R. Polynomials of order at least, or a maximum 7. So we have x to, and the coefficients are real, and x is real. Now let's just consider the linear map on that vector space to be T, which for this example, let's let this linear map be the differentiation map. The very first thing we need to ask is T an operator? If we have the differentiation map on R7 or P7, is it an operator? What do we need it to do to be an operator? If you have a 7th order polynomial and you differentiate it, you'll still, even if it's 6th order, you'll end up with a 7th. You'll still be in the 7th order polynomial, the set of 7th order polynomials, right? So it is an operator, this differentiation map. So T, I wouldn't have started this example if T struck out in the first swing, right? Maybe. So T is actually an operator. On V. Now we want to consider a subspace on V. Consider U equal to P sub 4 on is U a subspace of V? Are 4-dimensional polynomials a subspace of 7-dimension? Yes. 7th order, I should say. So U is a subspace of V. Now let's consider a vector in that subspace. And what's a vector? May not be a tall, thin column, is it? It's just a polynomial of maximum order. If it's in capital U, it's a 4th order polynomial, right? So now consider some U, and that's arbitrary, so it can be anything in capital U. What happens if we now apply this operator T to that U? Where does it go? It stays in U, doesn't it? Just like if we had V and did the differentiation, we stayed in V. So what can we say about U as a subspace? P4 is an invariant subspace under this differentiation map T. Therefore, P sub 4 is an invariant subspace under the given T. Well, maybe what I should, let me write that again a little bit more. P sub 4 is an invariant subspace of P sub 7 under differentiation, under that linear map T. And that's a little different way of thinking about these concepts. Instead of just always restricting or thinking about standard matrices, now we could have a matrix, but it would now be this maybe matrix representation of this linear map of differentiation. Let me ask a question sort of as an aside. What is another subspace of, let me introduce the terminology now. What is another subspace, let me call it Q, of P sub 7 of R, such that P sub 7 of R is equal to P sub 4 of R plus Q. What's Q? we want this sum of subspaces to give us all of P sub 7. P sub 4 just gets us up to 4. We need to sort of add on the next higher orders, right? 5, 6, and 7. If we now defined Q to be, let's say, a sub 5 z to the 5th plus a sub 6 z to the 6th plus a sub 7 z to the 7th, such that the a5, a6, and a7 are in real, that would actually be what we would need. Now, we have a little bit better feel for these invariant subspaces. Let's state some facts. Here are some facts. Let's just start with a linear map or an operator, T. The first fact is that the null of T is invariant. What do we know about the null space of that operator? We're saying it's invariant, and we're not even finishing that sentence. It's an invariant what? Subspace. So the null space of T is its own subspace. You find the null space of a linear map, and all vectors in that subspace stay in that subspace. Once you have that subspace identified. If that's the case, what can we say about the range of T? That also is invariant. We're trying to get some subspaces that we know something about that we can now start to relate to these ideas of things being invariant. Okay. Some invariant subspaces other than zero and V. Those are sort of trivial invariant subspaces, aren't they? If we start in 0, we're going to stay in 0 with a linear map. If we start in V, by definition of the operator, we remain in V. So that's also an invariant subspace. So invariant subspaces other than the 0 vector and the whole vector space must exist if A, the dimension of the vector space V is greater than or equal to 1, and our field of numbers are allowed to be complex. Then we could have another invariant subspace. B, dimension of V, and now pay close attention to that inequality. It's a strict inequality. The dimension of V is greater than 2, but now our field of numbers are real. And we're going to start understanding some of these facts a little bit better when we start remembering these concepts that we talked about with respect to Chapter 4 and polynomials. Let's now start talking about, so this second 3b, notice it's not 2b, this is 3b, 2b or not to be, this is 3b, sorry. So this is 3B. When we're dealing with a field of real numbers, then we have to have, if we want an invariant subspace, guaranteed. If they must exist, then we have to have our vector space being bigger than 2. Because we just gave an example where I could give you a 2 by 2 matrix that does not have any eigenvectors or any real eigenvalues, so it does not have any real eigenvectors, and we need eigenvectors to give us this invariant subspace. That's why we have this strict inequality on part B. In part A, as long as we have a non-constant polynomial, a first-order polynomial with complex coefficients has a root, that's why we can have the vector space V being greater than or equal to 1 when we have complex numbers. Then we do have eigenvalues of just a single dimension. Let's look at or talk about now studies of 1D invariant subspaces. This is actually the simplest kind that's interesting. Suppose that we're now given a vector u in V. So that just means we're starting with some vector in our vector space V. And suppose that u is actually AU, where A is an element of our field. That's a scalar in our field. So now we have some generic vector space V. We've now built up a one-dimensional subspace, capital U, where that one-dimensional subspace is essentially just a scaled version of this vector little u. All scalar multiples of little u. Now what we want to know is, so what happens if u is indeed invariant? What does that mean? U is just a vector, or I'm sorry, the subspace U is some scalar combination of a vector U. So you could think of some line in two-dimensional plane, and that's now our subspace U. Suppose we are now given a vector W that's in U. Now it lies on that line somewhere. If U is invariant under a map, then TW stays in that U if W started in U. All we're saying really is TW is a scalar multiple of W. What does that say? Well, if TW is a scalar multiple of W, How can we write that? We can say TW is a scalar multiple of W. Well, the scalar we could just call lambda. And where lambda now is in our field of numbers. That should look very familiar to us. What are we calling some of these quantities? What have we called lambda? If it satisfies this equation, if this linear map just causes W to become a scaled version of W, then we call lambda an eigenvalue of this linear map T. If there is a non-zero vector W such that TW equals lambda W is true. That's the definition of our eigenvalue. And this vector W is called the eigenvector associated with that particular eigenvalue lambda. What that actually, another way of thinking of that is a 1D invariant subspace of this linear map T only exists under what condition? When is that equation going to be true? When we can find a W and when we can find a lambda. We need to have a lambda. So T has to have an eigenvalue for this relationship to exist, or for us to have a one-dimensional invariant subspace. A one-dimensional invariant subspace of this linear map T only exists if T in fact has an eigenvalue. And we've already learned how we can rewrite TW equal lambda W. We can rewrite that as T minus lambda I W equals 0. But that should look very familiar. We now have an operator operating on a vector mapping us to the 0 vector. What does that mean about W? That vector. That means that the eigenvectors of this linear map T corresponding to different lambda, if we have multiple lambdas, but let's just talk about the one, those vectors or eigenvectors are actually in the null space of this operator T minus lambda I. Thus, the eigenvectors of this linear map T corresponding to lambda are in the null space of T minus lambda I. But what do we know about vectors that are in the null space? if we have vectors in the null space, and I add those vectors together, any linear combination, what happens? They stay in that same subspace, don't they? So those form a subspace. This also means they are a subspace of V since the null space of any operator is a subspace of V. Which means that now we can think of an invariant subspace and so far we've just been talking about a restricted subspace, a 1D subspace, or a very specialized subspace, a 1D subspace as an invariant direction. Again, I said it was this line, so an invariant direction in the vector space V. And vectors in that direction they don't move off of that direction. They stay in that direction under or upon application of that linear map. Vectors in that direction don't change. Direction upon application of T. Let's look at some examples. Suppose I give you a linear map T that's A times I. What does that do for us? Well, let's look at if we can find eigenvalues and eigenvectors for this map AI. What's our eigenvalue eigenvector formula? That says that we need TW to equal lambda W. But what did we say T was? That's just AI. And maybe you're in that class. Sorry, artificial intelligence. That's usually a capital A and a capital I, but this is lowercase a. That's a scalar A times I. W is equal to lambda W. But that identity matrix can basically collapse away or become absorbed, and that last equation now says that we have AW is equal to lambda W. Does that tell us anything about our eigenvalue? We have only one eigenvalue for all of that linear map, don't we? And it's lambda equal to A. So we have the only eigenvalue for that linear map, which is the scaled identity map, is lambda is equal to A. What can we say about the eigenvectors? Which W satisfy this? Where W is in, let's say, a vector space V. How did we have to specialize W for this to be true? Did we say anything special or restrictive about W? W could be anything, can't it? Any vector in our vector space can serve as an eigenvector for this particular map. So that relationship, AW is equal to lambda W, is true for any vector in our underlying vector space V. Or stated another way, we could say all vectors in the vector space V are in fact eigenvectors. Or again, thinking in terms of direction, the direction of any vector W, let's say, is left unchanged by application of T is equal to AI. Let's look at another example. Suppose we have a linear map T, and now it's an operator. So what do we know has to be the size of our output, or the codomain? It has to be the same size as our domain. The domain was two-dimensional, W1 and W2. Suppose that I now tell you that this linear map is going to make the following output: minus omega 2, omega 1. What's that doing? That should look very familiar. This is a 90-degree rotation counterclockwise in the plane. We're dealing with a plane. So now let's say that we're given a vector W in F2. So now we're keeping W either real or complex. We're keeping it in F. And W, we're saying, has these two components, W1, W2. From our eigenvalue, eigenvector relationship, we now know that TW is equal to lambda W. And what does that say? What's the left-hand side if that's TW? If we go up to the defining equation for that linear map, we say that TW must be minus W2, W1. But we want that to equal lambda times the original vector W. What we're trying to do is we're trying to find lambdas that might allow this to hold. So let's look at the first coordinate. We really have two coordinates, and maybe we can use those to find what lambda needs to be. From the first coordinate, we know that minus W2, the second coordinate negated, must equal lambda times W1. And we could multiply that by minus 1 or both sides, and we now find that W2 is minus lambda 1. Is that okay? Now we know we have a relationship between W2 and W1. Let's look at the second coordinate. Second coordinate now tells us that W1 is equal to lambda W2. Now let's use the strategy that we've done before. Let's replace W2 in this second equation with this expression that we derived from the first coordinate, so that now we have W1 is equal to lambda times W2, but W2 was just minus lambda W1. So this now becomes minus lambda squared W1. Now we have W1, and that's supposed to equal minus lambda squared W1. Maybe that looks a little weird, but if we think of this as 1 times W1, then we can say, oh, we really have minus lambda squared is equal to 1, or lambda squared is equal to minus 1. And now think of what we have. If we let our field be real, do we have a solution? No, we already learned that. If we let the field be the complex numbers, then we can have a solution. We'll pick up at that point next time, but you might start looking to see what you can do with this in terms of eigenvalues and eigenvectors.